about data-driven surrogate models. The whole idea being how can we reduce the computational burden for some expensive simulations while still retaining some of the accuracy that we may need for design. And this talk is going to be like slightly different from a lot of the ones you've heard because it's not about a direct contribution to SU2 or its features. It's more application oriented about how we can use the open source suite for these types of applications. So just a general outline, talk about some motivations, challenges of the problem, what we hope to achieve within the context of multi-fidelity surrogate models. I'll spend some time talking about the methodology and specifically the transfer learning framework, which is what facilitates a lot of our solutions to the challenges that I will outline shortly. Some preliminary results and then conclude. So this is the question we've all asked at one point or another in working with some CFD solvers is how can we make this dang thing faster in order to use it for design applications or maybe gain some physical insights. Working with complex PDEs like the Navier-Stokes equations, we know that they're complicated. And oftentimes in order to resolve certain types of physics, we really need fine discretizations to capture some of the physical features that are present in flow features, in the flow applications. So these simulations can be quite slow and expensive, specifically when you need to resolve the smallest spatial and temporal scales. And in addition, for applications which require querying the solver multiple times, such as in the case of design optimization. So this is the main bottleneck for these, what I would consider classical numerical solvers that we work with. One possible alternative for this is data-driven surrogate models. However, they also have their own limitations. One being that they require immense amounts of data to train them in order for them to give you sensible physical results. And the training data takes a long time to generate because the computational solvers themselves are expensive, but we also need very high resolution data, again, to capture the physical properties that we're interested in, things like the conservation laws, Galilean invariance, and then of course the flow features that we are dealing with in the variety of applications that we have. So overall, large computational burden, both to generate the data and then to train the deep learning surrogate models to achieve the outputs and predictions that we want. But the idea of using these data-driven surrogate models has proven to be quite successful in reducing the computational cost while maintaining the relative accuracy of the solvers. Traditionally, they started with some classical techniques like interpolation, support vector machines, but more recently, of course, the deep learning approaches are at the forefront. So in this particular work, the authors were solving the Rayleigh-Bernard convection problem, where you have a cold plate at the top separated by some distance with the hot plate on the bottom, and then you have these buoyancy-driven effects that evolves the flow in time, sort of like the vertical features that you see there. So in their approach, they have a high resolution baseline ground truth from a high fidelity simulation on a really fine grid. Their model input is some coarser grid simulation with a relatively coarse discretization. And then the output of the model is, again, it aims to recreate this high fidelity prediction. And here, in the second work, it's very similar. So they have, here we see like a vorticity field. And so these authors were trying to reconstruct the detailed fine scale turbulent flow features that would be predicted by a high resolution solver. So in this case, it's a 5,000 by 5,000 roughly computational grid. In the middle is their low fidelity model that's predicted by their surrogate model, which is only 128 by 128. And then this is a coarse CFD grid itself. And you can see the time evolution of the flow features. In this last work, these authors were trying to reconstruct the flow features from the low fidelity data coming from Euler simulations whereas the high fidelity data is the RAND simulation. So they apply some surrogate models to reconstruct the flow features, and they're essentially trying to learn the mapping from the low fidelity to the high fidelity. So our work is primarily motivated by some of these things here. So in this work, they applied this problem of super resolution, which essentially you can think of as from the image processing and computer vision community, where if you have a really coarse pixelated image and you want to have the higher resolution equivalent of it, how do you achieve that? But we're interested within the context of physics-based simulations. What they did was they created a surrogate model to accelerate simulations, essentially. So they have some low resolution input training data. The model predicts the output high fidelity flow field. And here you see it's compared to the high fidelity CFD ground truth. And the whole point is if they can provide this relatively cheap approach, then they can use it as a way to initialize the CFD solver and speed up the computation there. And the main idea being that the model is trained primarily on low fidelity simulations, which are much, much cheaper than the high fidelity. Here in this work, it's a similar idea. So these authors focus on physics constrained super resolution networks for turbulent flows. So traditionally, the work that has been focused on finite dimensional mappings, so images which have this finite number of pixels. However, these authors are trying to extend that to infinite dimensional function spaces, which are critical for solved PDEs. So having certain properties like integrability, continuity, differentiability, and so on. These are things we require in the solutions of PDEs. So they solved it for a variety of flow problems, but here you see another turbulent flow problem where they initialized with some vorticity field, and you can see the time evolution over 30 steps. Here is the ground truth, high fidelity ground truth, and here's the model prediction. The important thing here is, as I mentioned, we want to recover the physical flow quantities like the turbulent kinetic energy, dissipation, Kolmogorov scales, etc. So what are the main challenges here is that we want to use low fidelity data, but they don't have a lot of the physical features. For instance, going from Euler to RANS, we introduce viscosity. Going from RANS to even high fidelity like LES, we resolve the finer scales. So that is a challenge in the low fidelity data. And we can run these high fidelity simulations, but they require immense computational resources and a lot of time to really capture the physics that we're interested in. So they can be prohibitively expensive, especially when it comes to training these surrogate models. So we're trying to address this issue of the computational burden. So we're applying this idea of transfer learning, which I will detail shortly what that means, to develop a multi-fidelity surrogate model for predicting high fidelity flow fields with affordable training time. And in this case, multi-fidelity consists of a coarser grid and then a finer grid, which is indicated by the higher fidelity. So importantly, we want to construct flow quantities, aerodynamic functions which are crucial for our design applications, which is ultimately what's motivating this work. And eventually we can hope to reconstruct some fine scale turbulent flow physics. So in terms of our test case, we started with the classic quick start NACA 0012. We simulated it for a range of Mach numbers from 0.3 to 0.7 and angles of attack from 0 to 5 degrees, with the total about 150 different case combinations. We used the RAND solver with the Solaris turbulence model. And in terms of our grid resolution, we had five different options ranging from 10,000 grid points at the coarsest mesh to 2.5 million at the finest mesh. And one thing to emphasize here is that a lot of this was made possible by the advancements in the Python wrapper that we've worked on and that Pedro highlighted recently. These machine learning frameworks require a Python interface, so the fact that now SU2 has a really flexible modular framework really makes this quite possible. So going on to the idea of transfer learning and our surrogate model network. So we use an autoencoder architecture where we have some encoder layers that are denoted by green boxes, and then a decoder layers denoted by the yellow boxes. So we have 4 layers of the convolution layers in the encoder, which are extracting the physical flow features from some input image. And then it recreates like a hierarchical representation of the key features in that image, things like the weight, the boundaries, and so on. So it creates a latent space representation, simplified representation that you can kind of think of it as like POD modes coming from like SVD or something. Then the decoder aims to reconstruct that initial input image from those few modes or features that are in the latent space. So we want to reconstruct that image from start to finish. And the key thing here is that we have nonlinearities present that we can model due to these activation layers, which in this case is a leaky ring. So transfer learning is essentially taking some input from a source domain, and then we're trying to apply that to a target domain, which we hope to model. In this case, are the higher fidelity images. So in phase 1, you take the training, the network is done by providing an input coarse grid flow solution, and then the output is that same coarse grid flow solution. So we train the network to try to reconstruct that image. In phase 2, we repeat that same process, retrain the entire network, but this time with high fidelity images, with being the inputs, and then we aim to reconstruct them as the outputs. Then finally, phase 3, it combines the outputs from phase 1 and phase 2, the weights we have learned in the model. So the encoder portion comes from the phase 1. So we take the input to the low fidelity, pass it through the encoder weights that we learned in phase 1. And then we have the decoder portion that comes from phase 2 that reconstructs it with the high fidelity images. And here we have this additional block that's doing the super resolution problem that I sort of hinted at. I won't go into the detail here, but that's the general idea. The total training time for all 3 phases is about 10 minutes. Yeah, the 3 minutes for phase 1, 3 for phase 2, and then 3 or 4 minutes for phase 3. So in terms of some preliminary qualitative results that we have, so to our network, we provide, again, the input as low fidelity, and we want to construct high fidelity. So this is the target density flow fields, and this is what our model predicts. So qualitatively, they're quite similar, both at 0 angle of attack, 5-degree angle of attack in both cases. But you see some unusual business at the far field boundaries, and that's due to some treatment of the boundary conditions that we're still working on. But generally, it looks promising. Also, when we consider the momentum fields in the XY direction for the 2-degree angles, this 2 different angles of attack. If we take to better assess the differences in the target and the predictive fields with the model, here's showing the normalized density field differences at a range of angles of attack. And this really highlights the issues that we're facing at the treatments of the boundary conditions. So that's ongoing. But generally, these errors are within like 0.15 roughly in all of these cases. Same type of density differences for a different range of Mach numbers. One thing to highlight is this is sort of misleading. The colors are kind of skewed by the scales in these plots not being all normalized at the same contour color. But the bounds that we see plus or minus are roughly equivalent. So, I mean, this figure needs to be updated. But so the general idea, to summarize what we've been working on, is we wanted to address the question of how we can speed up simulations while retaining some of the accuracy by leveraging data-driven techniques. So we constructed a multi-fidelity surrogate model to predict high fidelity flow fields in an affordable training time. And we applied transfer learning to do so. So something that are ongoing, specifically related to the information that we're leveraging from SU2. So far, we've worked only with the primal solver and the conservative flow fields, but then we're going to be, the next step is addressing some of the adjoint solver capabilities, again, through the Python interface. And the benefit of introducing some of the adjoints in the training data is that the adjoints implicitly already have some type of spatial encoding in it, which can help us with the grid invariance problem, because we ultimately want to scale this up to arbitrary grid resolutions. And specifically on the transfer learning framework side, treatment of boundary conditions, introducing more physical constraints without inducing something like the loss function, where you have some regularization term, because we don't want to have that as being a physical constraint from the solvers. The grid dependence thing I've mentioned, and then lastly, the results we've seen are based on convolution neural networks, which operate in finite dimensional spaces, but we're hoping to extend these techniques to learn the mappings of entire solutions of PDEs in infinite dimensional function spaces. And we can do this with these new techniques called Fourier neural operators. So thank you for your time, and I'll take any questions. Thank you.
Thanks for the next presentation. Can you give an estimation on what the meetings you have? Because you say you have these, obviously you need a large amount of data if you go the normal route, and you substitute these traits, and algorithms, and what are the savings like?
Yeah, so short answer, yeah, sorry. Right. Yeah. So the short answer is we didn't have opportunity to do the quantitative comparison with the speedups. But the way these transfer learning things work is you're training largely on the low fidelity data, and then you train the network to keep the weights the same, transfer to phase 3, and then you train on like maybe 20% of the high fidelity data, or maybe even less. So you get some savings from not having to have your entire training data set come from the high fidelity, but also then in the training the model where you're preserving some of the weights for the final network. So for the future work will be to quantify the speedups, but what those are.
For training, they use only one airflow shape, only the one test case on the main angle attack, and is it possible to extend this to different airflows?
Yeah, totally. Yes. So you can
are we training the model or the same model you use for this?
You would require retraining because the features that you will learn in the model might be separate, but it's worth trying having a model on the academic call case and try it on a different airfoil. But I think it requires retraining because the full features might be separate.
So they will more. Because how do you generate the training data set? Like random points or do you have competing criteria?
Yeah, so the bounds I gave for the mod and angle that you just implemented between those through the Python macro. Yeah, exactly. So you saw it all subsonic for the moment, and we didn't even quite go into the transonic region, but we hope to extend that in the future. So right now, this is a lot of proof of concept, making sure the pipeline is working properly. But we're going to try to push the limits to capture more of the flow nonlinearities, the transonic case, and see how it also behaves supersonic. And different geometries as well.
And then we have here the variables test.
So thank you very much for the presentation. I was just wondering something maybe similar to the question that you asked. So I was wondering, if you change the periodicity, different pressure temperatures, the probability may be reasonably well different. So would that require retraining of the data set that's on the ISO? And do you think there are any possibility to make this video robust with operating conditions such that the same model can be used to different operating conditions?
Yes, I think it would be easier to generalize to different operating conditions than it would be to different geometries. So maybe it would be easier to try different far field Mach numbers for angles of attack rather than the different geometries. Yeah, it is possible, but I think a lot of it will require retraining the model in order to capture maybe the differences in the features.
I see. So the end goal is not really like making a tool that is, well, general, and just sell and people can use for different applications, like for case.
No, absolutely not. The goal is to just not replace, complement maybe some CFD solutions with like a relatively cheaper model that you can test for design problems. Like design space exploration is the main application that we sort of have in mind. So in maybe conceptual aircraft design, for example, or airflow design, if you can just query the surrogate model multiple times in a rapid fashion without needing the full high fidelity accuracy that would be able to do. But that's the intended application.
Okay. Let's make Asha then.